Okay, welcome everyone. I want to take y'all through um, a little exploration of linear independence and span. This is a series of exercises that when I can, when opportunity permits, I like to do in class. But this semester, we do not have that opportunity. So anyway, here we are. So I'm going to share my screen and dive right in. Um, so here it is. So the question that, again, when opportunity permits, I like to do this in the think, pair, share format. Can't do that this term. So if you have three vectors in R2, is it possible for that list to be linearly independent? So that's the question that we want to entertain. I want to take a couple of different points of view on this. On the one hand, there's a sort of a geometric point of view. You can sort of think it through in terms of how this might point in that direction, and how might you be able to get linear combinations to add up to zero, stuff like that. And then we're separately going to consider an algebraic point of view on the same question. Then we're going to kind of compare and contrast pros and cons of those two perspectives. We'll move on later to what happens if I have four vectors in R3. Okay, so let's start though in 2 dimensions, looking at three vectors. Can they be independent? Okay, well, we're going to start with geometric point of view. I'm just going to draw some pictures and kind of think it through. There's going to be a first vector, right? So let's say that first vector is, well, just to get it out of the way, let's entertain the possibility. What if that first vector is the zero vector? Could the zero vector be part of a linear independent list? And I say no, because 0, comma v2, comma v3, I can always multiply that by 1 and then the other two by 0. Now look at my coefficients here. My coefficients are significant, right? This is a significant linear combination, and yet it adds up to the 0 vector, right? So you can see this little trick, right? This little smart alecky move here. This is always going to work. And whenever 0 is part of your list of vectors, it's just not going to be possible for that list to be independent. There's always going to be a relation. Here it is. There's the relation. Okay, so no 0 vectors. All right. So, okay. All right. Well, now we have that silliness out of the way. Let's consider other possibilities. Let's suppose there's my first vector. Now, the second vector, I could try to save space and make that second vector like this. Make it a multiple of the first vector. In some sense, then I haven't used up all the space. But can I do that? I mean, if I want this to be a linearly independent list, I need, well, different ways to say it, but I need none of the vectors to be a combination of the others. I need none of the vectors to be a multiple of the others. So you can't do this, right? That's not allowed if you want your list to be independent. So, okay, fine, no problem. We've got plenty of space. I'll just make the second vector over here, right? So we seem to be doing okay. We've realized the first vector can't be 0. The second vector can't be a multiple of the first vector. But now we have this problem. Where does the third vector go, right? So keep in mind, we're trying to form a list of 3 vectors in R2 and maintain independence. So, well, that third vector, here's the thing. See, I can't go parallel to the first vector. I can't go parallel to the second vector, but the big problem really, I can't go in any direction that's a combination of those. So for example, if I were to try to make my third vector, let's say this, well, that is a linear combination. That's, it's about that much, a little bit of a multiple, a little bit more than 1 of a multiple of the purple vector, and then plus, what is that about, well, again, a little bit more than 1 multiple of the second vector. And so this here, this orange vector is a combination of the first 2. That this is not an independent list, right? And likewise, in some sense, there's no way around this at this point. Let's look at any vector, whatever vector I might be How about this one down there? Right. Well, that is going to be some multiple of this first vector. Looks like about that. Oh, it's a negative multiple of the first vector. Sure. Plus, well, some multiple of that second blue vector. Right. And sure enough, therefore, that orange vector is a linear combination of these first two. So this kind of an argument, you can see we've sort of run out of possibilities, right? We've showed that no matter there's only so many options, various different cases, either this is zero or not zero, or this is a multiple, or this is not a multiple, and we keep eliminating possibilities. We have now eliminated all the possibilities. No matter what you do with your first two vectors, you will have painted yourself into a corner, if you will, and there's no way to make that third vector maintain independence. Okay. All right, so going back up to the original question, this is what I'm going to call the geometric point of view on this question of whether it's possible to have a list of three vectors independent in R2. There's something nice about this geometric point of view. We can see what's going on. It's geometrically intuitive. These are all good things. I'm going to show you instead now an algebraic point of view on this. And the algebra is always a little bit more abstract, a little bit less relatable. But not another way to say that is it doesn't it doesn't satisfy your intuition, but it also doesn't rely on your intuition, right? There's something about geometric intuition that's intrinsically kind of suspicious, right? We're always kind of trying to persuade ourselves on that. So let's instead take an algebraic point of view. Here we go. Independence of a list of three vectors is described by looking at this equation, right? Specifically, this is what a relation would look like. And to be independent, we need to know that there are no significant relations, namely no significant solutions to this system. Okay, now let's just rewrite that a little bit. All I've done here is make the observation that each one of these vectors has two components. Why is that? Well, we're looking at vectors in R2. Right, so each vector has two components, calling them here A1 and B1. Okay, here we have what you might call a vector equation, but if you multiply that out, you get a system of equations. It's a little 2-row, 3-column, so 2x3 system of equations. All right, we have a notation for how to write systems of equations. We have this. So we need for this, chapter 1 style system of equations, again, to have no significant solutions. Okay. Okay, how do we answer these chapter 1 style questions? Now let me, I guess, maybe observe real quick before we go on. We have turned a chapter 2 question into a chapter 1 question, right? So we've made significant progress just by writing down a definition, right? And reinterpreting, we've translated the question into a much more familiar kind of a question. What can we do with systems of equations? And here we have a nice simple answer. How do you know if solutions exist? Well, we take the system and we row reduce it. Specifically, we look at the coefficient matrix. Conveniently, this is homogeneous. So if I want to know if there's significant solutions, I already know 0 is a solution. If I want more than just that trivial 0 solution, that means I want multiple solutions. That means I want for the solutions not to be unique, right? So what we're looking for is if there's going to be significant solutions, if this list is going to be dependent, I would need for there to be a free variable. And so let's just count now and see what we have. Where can the pivots be? Well, I could have a pivot in the first row, maybe there, maybe here, who knows? And then, I guess I could put a pivot somewhere in the second row. I don't know exactly where it's going to be. There's various possibilities. What I can see for sure is that there's at most 2. because I only have 2 rows. That means they're going to be at most 2 pivots. Um, and with only 2 pivots, I don't know where those 2 pivots are going to be, but I do know for sure that there is going to be a column, one way or the other, that does not have a pivot. And that means that this matrix does not, whoops, typo, does does not have the uniqueness property, right? Um, right. So the question, as um, we wrote this about independence. Independence would mean that the only solution is the trivial solution, so no significant solutions. And we can see this is not possible, right? So having the uniqueness property, having a pivot in each column, not going to happen. We only have 2 pivots. We have 3 columns. Okay. All right. So what's nice about this algebraic point of view is it doesn't rely on having some geometric intuition. It doesn't really hardly boil down to there being cases. I suppose technically there's the matter of, well, there's pivots could be here and here, or the pivots could be here and here. I suppose those are cases, but I don't even really need to worry about that. There's a simple matter of there's clearly at most 2 pivots. And with at most 2 pivots and 3 columns, there will be a column with no pivot. There will be a free variable. So it is not possible to have the uniqueness property. Okay. All right. No geometric intuition required. Okay. So now let's go back up here. We've considered 3 vectors in R2. Let's move on now to a sort of a step up. What if I have 4 vectors in R3? So this is a geometrically more challenging question, right? First of all, we're drawing in 3 dimensions at this point. 3 dimensions, right? It's hard to draw on a 2-dimensional piece of paper. And it's hard to sit there and build actual 3-dimensional models of vectors and be doing like this all the time and trying to see all the different ways that vectors can combine in space. So this is geometrically now a much harder question. And we can still play through and think about, if you have 4 vectors in R3, we can still go through and think about the various different cases, such as, well, we know we can't have the 0 vector. Right? Okay, so that first vector we'll say maybe is like that. And then the second vector, again, can't be a multiple of that. So maybe it points over here. Now here's where it gets kind of harder. The third vector, well, I can't have that third vector be a combination of these 2 vectors. What would it mean to be a combination of those first 2 vectors? My intuition that I'm going to try to pitch to you is that being a combination of those first 2 vectors would be a plane, right? I think that's pretty believable, but you got to really persuade yourself that. And then furthermore, that's what the third vector cannot do. So you have to have the intuition to realize that a plane is not all of R3. And there is some other direction over here that is not in that plane. And well, now there's some geometric ideas that we're kind of using our geometric intuition there. There's this urge to say dimension. There's this urge to say that the plane is 2-dimensional and that space is 3-dimensional, and that therefore there's another direction to go. Right. So it's this, we have this sort of intuition, but it's getting a little sketchier. Right. Then furthermore, how do I know that it is not possible to make a 4th vector and maintain independence? Well, we have a tough geometric case to make here, right? Really hard to see how it's necessarily the case that this vector over here, for example, how can I really see working on this 2-dimensional screen, right? Trying to visualize 3 dimensions with 2. How can I see that this must be a combination of those? This is getting harder. And you can maybe persuade yourself that you can think that through and you can consider the cases. How do you know that if that third vector is not a combination of these, then it must, have a component in that direction? It's a hard argument. Notice we don't need that, though. Right? The beautiful thing about this is the reason I wanted to look at the geometric point of view here is to see how it's kind of undesirable, and yet the algebraic point of view is the same, right? It's hardly any harder at all. Viewed algebraically, we're still entertaining independence. The way you arbitrate independence is by looking at relations. We can still write down relations, 4 vectors instead of 3, fine. You have 4 vectors instead of 3, then there's going to be 4 terms there. And each one of those terms, of course, gave rise to a column. So we'll just have 4 columns in our eventual matrix. That's it. It's an easy adaptation. Furthermore, now we're in 3 dimensions instead of 2. Okay, well, up here, because we were looking at 2-dimensional vectors, we had 2 entries in each column in our eventual matrix. Okay, being as we are here in R3, stands to reason we should now have 3 entries in each column, aka 3 rows. Right? So it's easy to see how this argument adapts. It's morally the same argument. Adapted appropriately, we see that in order to be independent, I would need to have a pivot in every column of this matrix. And again, that's not possible. You just can't do it. There aren't enough rows, right? And if not enough rows, right? We only have 3 rows, means there can be at most 3 pivots. We just don't have enough pivots to have 1 in every of 4 columns. Okay. All right. So really nice to have that algebraic point of view when the geometric point of view started to get harder. Okay. All right, so that's the first question I wanted to talk about. Now there's a very closely connected question that I want to do next, and I always do these as a pair when we're talking about these in class. So here we were talking about what I'm going to call, if you will, loosely speaking, too many vectors, right? 3 vectors in R2, 4 vectors in R3. Speaking loosely at this point, I think you kind of probably have a sense of that this is too many vectors in each case. Exactly why, we'll make precise a little bit later, not today. Beyond what we can say here is that, well, there's too many columns, right? Okay. All right, we're going to find a better way to say that soon. So anyway, what we're going to be looking at now is, instead of independence, we're going to be looking at this question of span. Is it possible for a list of vectors to span R3? And here, instead of too many, we're going to be considering the case of too few. Does that work? Okay, so these are geometrically pretty different questions, right? Independence is about whether I can think of one of them as being a combination of the others, whether I can think of them kind of the directions being sort of overlapping in some sense, if you will. Here with span, nothing of the sort. Here we're trying to ask just the question, can I generate everything in space as a linear combination of our given vectors? And so, for example, here's 3 vectors in space. Do these 3 vectors generate the entirety of R3? They seem like different geometric questions. We can still play through and try to take a geometric point of view on this. It's going to seem like a pretty different argument. We're also going to look at the algebraic point of view, and that's where we're going to see some connections. I'm getting ahead of myself. So let's think about the geometric point of view first. I've got 2 vectors in R3. I want to span as much as I possibly can. Why not? And so that first vector, it'd be silly to have the first vector be the 0 vector, right? You're not spanning anything. That doesn't help you generate vectors with linear combinations. You can't generate anything with a 0 vector. So that first vector, you would think, should be non-zero. The second vector, now again, there's cases, I suppose that second vector could be in the same direction. Does this span all of R3? No, this only spans a line, so that didn't work. Okay, well, let's try something different then. What about instead of a parallel vector, what if I try a vector that points in a different direction? Well, that's going to generate a plane. My geometric intuition sort of suggests to me. Is that all of R3? Well, I don't feel like it is. Not sure how to say that precisely. I can make it appeals to this intuition I have for the idea of dimension. I haven't really defined dimension yet, so that's a little uncomfortable to say, well, it can't be everything because of some concept that I can't write down in words, right? That's unsatisfying. And you could say, all right, well, yeah, that doesn't generate this vector. Give me any two of these vectors and I can tell you what you missed. You cannot generate that green vector. At which point we have this problem of the opponent could then say, okay, well, then I'm going to change my second vector. And having changed my second vector, okay, now maybe that generates all of R3. See, now I've got that green vector you made up. Okay, well, then, yeah, but you didn't get that vector now. And you can see this can get a little hairy. I can keep chasing vectors and square peg round hole sort of a situation. And I think this is not going to work, right? I think that you just can't do it. But how to make this precise is very reliant on geometric intuition that we just can't make precise. So, look, I think this is persuasive, but I don't think it's rigorous. And it has holes in it, and it's a little uncomfortable. So let's take the algebraic point of view instead. And now what you're going to notice is that even though the questions are different, right? So here we're talking about span instead of independence, geometrically different ideas. We're going to find that the arguments smack similarly, not the same, but they kind of break down in analogous ways. So here we go. Here's what span means. Right? Span means that for every right-hand side, no matter what vector you want to generate as a linear combination of our first two vectors, right? There is some way, there is some linear combination, some way, some solution there, some set of coefficients that allow you to generate that green vector B as a linear combination of V1 and V2. That's what it would mean for V1 and V2 to span all of R3. Okay, so again, writing that out in components. Now, don't forget, we are now in R3. Being as we are in R3, these vectors have 3 components instead of 2. Last time we were thinking about 2. Okay. So, all right, we have this vector equation. Well, I can work this out sort of line by line, right? Write this down. We get a system of equations. We have a convenient way for writing systems of equations. It's matrix notation. This is the corresponding matrix notation for that same set of equations, right? Still haven't really done anything. And again, what we need in order for this to span, we need for this system to have a solution for every right-hand side, no matter what the right-hand side is. So said differently, I need for this coefficient matrix to have the existence property, right? This coefficient matrix, no matter what the right-hand side is, I need to know that a solution exists. And of course, chapter 1 tells us another way to say that is that means I need a pivot in each row. Can I possibly have a pivot in each row? Well, where could the pivots be? I guess I could have a pivot there and a pivot there. I suppose it's possible that I have a pivot here. Well, then I wouldn't have anywhere else to put a pivot. There's only so many cases. These cases, again, don't even really matter. What's blindingly obvious is I have clearly 2 columns only. You can have only one pivot per column. So it's immediately clear that I have at most 2 pivots. And if I have 3 rows, I cannot possibly have a pivot in each row. It's just not going to happen, right? So I cannot have the existence property, and therefore it is not possible for these vectors to span. So this argument here does not rely on geometric intuition. This stands comfortably alone, this algebraic point of view. Spanning is not possible. Because 3 is bigger than 2. I mean, that's what it boils down to. No intuition required, right? I mean, crushing grip of reason there. Compared to up here, well, you know, the arguments about hand waving, and we'll see these vectors and they make a thing that's 2-dimensional, which is not the same as 3-dimensional, whatever that means, right? So a much more rigorous, much more powerful argument here with algebra. Okay. All right. So let's consider now, before we go on here, you know, how do we generalize this? We kind of skipped over this previously. So talking about independence, right? The argument was our matrices are going to be, if you will, short and wide, right? If we're considering, if you will, too many vectors, right? Each vector represents a column. The dimension that you're in, each dimension that you're in represents a row. And if you have too many vectors, that means you have a short wide matrix. And in this case, the point was that 4 was bigger than 3. Wrong one. 4 is bigger than 3. And therefore, you cannot have a pivot in every column. You're going to have a free variable. This generalizes super well, right? It doesn't have to be 4 and 3. It doesn't even have to be n and n minus 1. You can have, as long as the number of vectors that you have is greater than the number of coordinates in each vector. The same argument works. So this generalizes to 7 vectors in R5, 28 vectors in R13, etc. Right? Very powerful that this generalizes like that. And then notice down here, same thing. Here we have tall, skinny matrices. And well, it generalizes in kind of the same way. It boils down here to the number of vectors that you have represents the number of columns. And as long as there are more coordinates in each vector, and therefore more rows, then there's going to be a row with no pivot, and therefore not possible to have the existence property. Okay, so the algebraic arguments generalize wonderfully. The geometric arguments, not so much, right? So let's go back. We can kind of handle the geometric argument in 2 dimensions. That was fine. You know, cases and stuff. 4 vectors in R3 started to get tough. Our geometric intuition was kind of stretched to the limit there. Certainly, at a minimum, there'd be a lot of cases, right? But we couldn't begin to pretend to be able to make a geometric argument about what happens if you have 28 vectors in R13. Right? I can't begin to visualize R13. That's just way beyond, no way, right? I don't personally believe anyone can really visualize R4. I think people can kind of fake it. But even R4 is questionable at best, right? And certainly beyond R4, no, I don't buy it. So the algebraic argument, much more powerful. Okay, so I'm kind of already getting to my takeaways. What I want you all to get out of these examples is as much as we like geometric thinking, right? It's a good guide. Geometry is a great way to think through and get a sense for what's really happening, and that can suggest for you which way is likely the right way to go with your algebra. Wonderful guide. I love geometric thinking. I'm a big fan. And it's very satisfying. I mean, we feel like we understand something if we have a sense for the geometric perspective on it. And that's great. I encourage y'all to develop geometric points of view on things that we do in this class. All that said, We like it and it's useful sometimes, but algebraic thinking is much more powerful, right? I mean, it absolutely can do things that our geometric intuition just can't do. And furthermore, we can trust it in ways that we simply cannot trust our geometric intuition. Okay. So that's one of my important takeaways here. The second one, and this is just a sort of a point of view. I think this is satisfying. I'm going to start with the suggestion that rows and columns are connected ideas. And what I mean by connected is if you're looking at a matrix, I can think of it by rows, I can think of it by columns, but ultimately those are just two perspectives on thinking about the same thing. I'm thinking about a matrix, right? Rows and columns are just different ways of thinking about it. So connected ideas in that sense. Well, if you think about it, when we were thinking about the span question, let's not get ahead of ourselves. When we were thinking about the independence question, what we did is, having written down from the definition, we wrote down some algebra and we broke it down to a matrix needing to have the uniqueness property. And of course, the uniqueness property is a matter of thinking about the matrix in terms of columns and whether or not each column has a pivot. Okay. Whereas when we were thinking about the span question, wrote it down from the definition, got it down to a matrix equation, and we realized we needed the existence property. And we arbitrate that by whether there's a pivot in every row. Okay, so the idea here is these two questions, the span question and the independence question, seemingly these are geometrically different, right? We talked about that at the time. These seemed, from a geometric point of view, to be pretty different ideas. Their definitions, I mean, they both say the word linear combination, right? But other than that, they don't seem to be particularly well-connected ideas. But what we've seen is that they trace back to simply taking different, row versus column perspectives on the reduced echelon form and where the pivots are. So in the same sense that rows and columns are connected in that they, they're just two different ways of thinking about really ultimately kind of the same thing. It follows that span and independence, geometrically different though they are actually kind of connected, right? The algebra reveals how these ideas are connected really highly analogously to the way rows and columns of a matrix are, again, connected. They're just two different ways of thinking of the same thing. So I think that's really intriguing. And then, by the way, analogously, existence and uniqueness, right? They seem like two questions that have to do with solving a system. And so they're two questions on the same kind of general topic, if you will, right? But it doesn't immediately present itself how closely connected these are. Well, again, existence and uniqueness connect to rows and columns. And so in the same way that rows and columns are connected ideas, likewise, existence and uniqueness are connected ideas. So I think this is a really great example of this as well. You can come back up here and see all of this happening. Here we have independence, which boils down to uniqueness, which comes down to columns. And then in the span question, span comes down to existence, which comes down to rows. And note this, the very, very strong analogy in how those are laid out on the page, and the arguments are comparable. Okay, so I think that's another big important takeaway, that these are connected ideas like so, and that's a good thing to chew on. Okay, so I hope this has been a useful discussion, and look forward to seeing you all in class.